Hello, welcome to another Mathfolio video. This is a geometry midterm review. So this is roughly half a year's work in the geometry course. To download the packet that we'll be working on, please visit mathfolio.com/geomidterm, and that will get you the PDF file of all of the questions that we're working on today. Alright, so question number 1 in the packet just asks you to sign to say that you've read and understood these notes. Basically in geometry we want to be super neat and precise, so using a pencil, ruler, etc. super important. And this question also catches the students who don't read everything, so it's really important that you read everything. If question number 1 is to sign, then you can't complain if you lose points for not doing something simple like writing your name. Alright, so that was question number 1. Question 2, alright, this is where the work really gets started. This question asks us to plot point A. So point A is a -3, comma 1, so -3, we go to the origin, 3 back, comma 1 is right here. Must label it, this is point A. And we're going to perform the following transformation, which is right here, t2 -4. So this is a translation. The 2 means we go to the right 2, 1, 2, and then we go down 4 because it's a negative, 1, 2, 3, 4. And so this is our image, and so we're going to label it A prime. So this is question number 2. We move to the right 2 and down 4. Alright, question number 3. This is asking us to simplify a radical. So we learned about simplifying radicals earlier in the year. We've got to try and look for perfect square factors. So I know that this is the same as 16 times 10. Now that's good for us because 16 is a perfect square. We can take the square root of it. 10 cannot be broken down anymore because even if you tried to separate into 2 times 5, we can't square root either of those prime numbers, so we would just put it back together as radical 10. However, square root of 16 is 4, so that gives us 4 radical 10. And that's our final answer for the simplified radical of square root of 160 becomes 4 radical 10. Okay, question number 4. This time we are being asked to state if a triangle with these 3 sides is a right triangle. So what we would do is we would first draw it, not necessarily label it as right because we don't know, but if it was a right triangle, the longest side would be on its own. So I'm just going to label this, and what we're really checking is if the Pythagorean theorem works. So we're trying to see if this works. So 4 squared plus 5 squared, does it equal, question mark really, does it equal 6 squared? So 16 plus 25, does it equal 36? And very quickly we're going to find out it doesn't, because 41 and 36, they're not equal. So none of these things are equal, so we can make the statement therefore with 3 dots, therefore the triangle is not a right triangle. And so that's question number 4. Okay, number 5, it's another transformation question. It's asking us to plot B, which is at 5, 3. So 1, 2, 3, 4, 5, 3 goes up here. This is point B. And it says perform the following transformation, which is a reflection over y equals x. So I'm going to change the color, grab a pen and the line tool. So the line y equals x is right here. You should always really label these as well. So I'm going to label it y equals x, which is our line of symmetry. And then B is going to jump to here. So we can kind of see that this is where it goes. It goes 1 diagonally across the square to get to the line of symmetry. It does the same again. Otherwise, the other way that we can do this is see that this is 5, 3, and when we reflect over this line, we actually switch them. We switch these around, so B prime is actually at 3, 5. The signs didn't change, we just flipped the numbers. So that's our answer to number 5. Okay, number 6. So this question is about midpoints, but we're also given different segments. I don't see any coordinates, so this is really talking about a straight line. So I'm just going to plot a straight line. We don't know where. Let's just see. So given y is the midpoint of xc, so I guess we could put y here, and if it's the midpoint, we know that this bit equals this bit, and y is the midpoint of xz, so I guess we could also label those other points. So now let's label the distances. So we know that xy equals 13, so x to y is 13, and x to z, which is this entire thing, x to z equals 26. And because y is a midpoint and these two are congruent segments, we could also label this as 13 as well. So it says find yz. Well, that's exactly what we just did. You could look at this as segment subtraction postulate, where we take the whole thing, xz, and we minus xy, and that gives us yz. And by plugging in the numbers, that would be 26 minus 13 would give us yz, which is 13. That's number 6. Okay, question number 7. Again, this is another transformation. So we've got point C at -3, -2. So origin, go 3 to the left for -3, down 2 for -2. Label it C. And this time we are reflecting over x equals -1. So I'm going to grab the line tool. I'm going to plot the line x equals -1. So whenever we have a line like this, x equals -1, we're going to find -1 on the x-axis, which is right here. And then what we're going to do is we're going to draw a straight line straight through it. And this is the line x equals -1. Kind of looks like the y-axis just moved over. So we have to be really careful. It's easy to get this mixed up with a horizontal line. But anyways, this is x equals -1. So with point C, it's 2 steps to that line. So we're going to go another 2. And so this is where C prime is. And if we needed the coordinates, it would be 1, -2. That was question 7. Okay, question number 8. This time we have another segment. This is a segment addition postulate. So I'm going to plot my start line. Let's change the color. So the line that we are dealing with is B. Point B is between AC. So you know what? Let's label each of those points. So we've got point A right here. It's point A. C is the other endpoint, and then B is between them, but we don't know exactly where. So I'm just going to put point B off center. So if B is between AC and AB is 2x plus 3, 2x plus 3. That's AB, and BC is 3x, and AC, so the entire thing, a little crooked, let me fix that. The entire thing from A all the way through to C, grab the pencil tool, is 3x plus 13. So is it wanting us to find x or a different distance? It says find the length of BC. So we can find x first, and then we're going to have to plug it in. So the work is that the whole length AC equals AB plus BC. So here we go. 3x plus 13 equals AB, which is 2x plus 3, plus BC, which is 3x. So when we combine like terms here, we've got these two, it becomes 5x plus 3. And on the left, we just bring down the 3x plus 13. So we've got x's on both sides, so I'm going to get rid of the baby x, which is a smaller coefficient. This goes, we got 13 equals 2x plus 3. So the x is being multiplied by 2 and then added to 3. So we're going to undo the last thing we said. So that kills off these 3's. We've got 2x equals 10. X is being multiplied by 2, so we do the inverse, divide by 2. Whatever we do to one side, we do to the other. So we end up with x equals 5. Now don't forget, the question asked us to find the length of BC. So we've got to come back and say, well, BC equals 3x, which equals 3 times 5. We found out x was 5. So therefore, BC equals 15. And that's our final answer for question number 8. Okay, question 9, another transformation. This time we are plotting the point -5, 4. So that's right here. This is point D. And we are performing the following transformation, which is R and then a point. Now, sometimes when we're given the letter R, it could mean rotation or reflection. But for it to be a rotation, we need a certain number of degrees, like 90 degrees or 270, or in fact any number of degrees. So when not given the number of degrees, we're dealing with a reflection through a point in this case. So the point of reflection is -3, 3, so we're reflecting it through this point. And so one way to do this is to travel to the point of reflection. We go across 2 and down 1. So we're going to do exactly the same again, across 2 and then down 1. So we always drop down 1, and so this is our new point, which is D prime. This is the image of the pre-image, and if we needed the coordinates, it would be -1, 2, and that's our answer right there. Okay, question number 10. All right, for this question, we are given a certain number of degrees. We are rotating 90 degrees. And when it says this, we assume counterclockwise. Now, there is a little trick where we can take the coordinates of the point that we're given, and then we can apply a little change here, which gives us a new location. First of all, let's plot the points. So P is at 0, 0. Q is at 1, 3. R is at 5, 1. And it says plot triangle PQR. So really we need to join all of these up as well. So I'm going to join up the shape. And so right now we just plotted the shape. Now, one way that we can find out the new image is to apply the trick where we switch and negate. The other way is to visually do this. So P is going to rotate around itself, but this is one other thing. Sometimes we are told the center of rotation. If we're not told a point to rotate it around, we assume it's the origin. So in this case, P is at the origin, so it stays where it is. So P prime is exactly at the origin. Now Q, let's just change this to yellow to show these steps. Q is 1 over and then 3 up. So this is kind of tricky to see, but as this rotates 90 degrees counterclockwise, this 1 over and 3 up becomes 1 up and 3 over. So point Q is going to go right here, and that's Q prime. And for R is 1, 2, 3, 4, 5 over and 1 up. So that's going to become 1, 2, 3, 4, 5 up and 1 over. So point R is going to become right here, R prime. And that's it. We relocated all 3 points. And so now all we need to do is just join them up. This is our image. And we can kind of see how this is turned. One way to do this in an actual test is to put your finger on the origin and turn your page 90 degrees. So the top edge of your page that runs left to right at the top should now become the left side of your page, and then you can see how it's become in the same place. Now, earlier I did talk about this little trick right over here that we could use, and because we've got these set up here, up at the top, the points, we could also get these set up straight away, and we could apply the trick. And so whereas Q was at 1, 3, what we end up doing is we switch and negate. So whereas it's 1, 3 before, it's now -3, 1. So look what happened. We switched the x and the y, and we negated the first value. That's the -3. Now, when we switch and negate, we get the 0, 0. But when we switch here, it becomes 1, 5. But then we negate the first value. So the rule when you rotate 90 degrees is that you switch them. The xy becomes yx, but then you negate the first. So if you can remember this rule, then you could just do these 3 points first, and then you could plot them and then join them up. Otherwise, the yellow lines show visually where each of these points transform to, where they rotate to. So that was question number 9. Or rather, that was number 10. Okay, so now this is number 11. Alright, so it says find the missing leg of a right triangle. So from the get-go, we are told it is a right triangle. So I'm just going to sketch this. It is a right triangle. We're trying to find a missing leg. So it can't be this longer side, because that's the hypotenuse. We're told the hypotenuse is 12, and the other leg is 6. So because we're told it's a right triangle, we know the Pythagorean theorem is going to work. So we just plug in these numbers. X squared plus 6 squared equals 12 squared. So x squared equals, x squared plus 36 equals 144. We minus the 36 from both. You get x squared equals 108. So what we've got to do is square root both sides, and we get x equals radical 108, which we could simplify. 4 goes in there, but it also, looking back, it tells us to round to the 10th place. So I'm just going to grab a calculator and try and get that answer to the 10th place, the square root of 108. And the square root of 108 is 10.4, so I'm going to label that answer down here, equals 10.4. And it is to the 10th place, so that is our question 11. Okay, question number 12. Okay, so we see from the diagram that we're given parallel lines cut by transversal. Right here, this here, and this here are the parallel lines. We know they are because we have these markings. They're called feathers. And this here is the transversal. So it says make statements and give reasons about the given angles below. Well, the statements are actually given for us here. Angle 1 is congruent to angle 4. And when we look, 1 and 4, because the reason is vertical angles. That's the reason, because they're opposite and equal, this and this. Vertical angles. Alright, let's change the color. Next, measurement of angle 4, which is right here. Measurement of angle 4, and the measurement of angle 6, right here, is 180 degrees because they are same side interior. Same side interior angles. So that's our reason. Okay, next, 7 and 6. Well, 7 is here and 6 is here. So it's the same reason as A. They are vertical angles, and vertical angles are congruent. Next, I'm going to change to orange. We've got number 1 and 8. Well, 1 is up here, 8 is down here, so they're opposite sides of the transversal, so that means alternate. They are not inside here, this would be an interior. So if they're not interior, they are in fact exterior. So alternate, exterior angles. Now 4 and 8, let's take a look, changing this to pink. 4 is here, 8 is here, and those two are kind of like in the same location, just at a different intersection. So they're both bottom right. So in that case, they are called corresponding angles. All right, the next one, 3 and 6. Well, 3 is here, 6 is right here, so they are interior and they're alternate because they're on either side, so therefore they are alternate interior angles. And the last one, G, the measurement of angle 5, let's switch color here, let's go for purple. Measurement of angle 5 right here and the measurement of angle 7 equals 180, and that's because they're a linear pair. You could also say that they're adjacent, but linear pair means that they're going to sum to 180 degrees, and you could also say that they are supplementary. They're supplementary, they add to 180. That was question number 12. Okay, 13. This looks like another transformation problem. So in this case, we've got VWX. V is at 4, 4. W is at 2, 4. And X is at 0, 0. It does say it's a triangle, so we should join it up. And so we're getting this triangle here. It says perform the following transformation, dilate with a scale factor K of 0.5. So what this means is, especially because we don't see a point after this, we're dilating with the center at the origin. If we were given a point, we would have to do a few other steps. This is slightly easier. All that we have to do is take the scale factor, which is 1/2, and multiply it by each of these points. So we have V 4, 4, we had W 2, 4, and we also had X, X at 0, 0. So when we times them by K is 1/2, okay, X, let's get everything ready. Be a little lazy here, so we don't have to think while we're just setting this whole thing up. So 0 times 1/2 is 0, 0 times 1/2, 0. 4, 4 times 1/2 gives us 2, 2. 2, 4 times 1/2 is 1, 2. So now what we're going to do is we're going to plot these 3 new points, these primes. So X prime is at 0, 0. Same location, V prime is at 2, 2. And W prime is at 1, 2. And we should join them up because we started with a triangle and our image is also going to be a triangle. And so this is the answer for question number 13. Okay, question number 14 is looking like right triangle question. So we've got the distance from a bird on the top of a building. So it's not looking too straight, but it should be. This is our building. We got some bird up there. So here's the bird. Oops. Gotta get my pencil tool. Alright, worst bird ever. From a bird all the way to a squirrel on the floor. So here's my squirrel. I have no idea what I'm drawing right now, but this distance is 300 feet. That's what we're told right here. The distance from the bird on the top of a building to a squirrel is 300 feet. So I'm going to label that. I'm also going to label the number next to it as well. 300 feet. So at the moment, I could forget about all of these words because I've drawn it. It says if the squirrel is 25 feet from the base of the building. Alright, so let me label that now. It's not looking to scale at all, but this is 25 feet from the squirrel to the base of a building. So when it says the base, it's talking about right here. Okay, so keep in mind that 300 is way bigger than this 25, but it's not to scale at all. Also, at this point, we could also label that this building is 90 degrees to the ground, or at least it should be. And then it says, how tall is the building? So I'm going to do this in pink. It's talking about this distance here from the ground up. So effectively, if we take out the awesome pictures of the bird and the squirrel and the building, what we're really dealing with is a right triangle. Tidy this up a little. What we're really dealing with is a right triangle where we're trying to find one of the legs. We're given 25 and we're given 300. So basically x squared plus 25 squared equals 300 squared, and that comes from our Pythagorean theorem. So when you start to solve this, x squared equals 300 squared minus 25 squared. I'm kind of just doing everything together right now, so I'm going to one-shot this at the end, but when you square root it, square root of x squared gives you x equals radical 300 squared minus 25 squared. You could do this piece by piece, or you could just now put it all in your calculator. So this is question 14, and so the answer when you square root this to the tenths place is, let me just check here, 299.0. 299.0. Now the reason why we need that 0 is because it does say to the tenths, and so really we should show it. You know, not the end of the world if we don't. But one thing that we got to notice at this point is how similar this 300 for the hypotenuse is to the height of that building. And in a way, that's because this squirrel is really much closer to the building than what we first drew it. So the closer the squirrel gets, the closer that this hypotenuse becomes the same as this leg. So anyway, the answer to number 14, 299.0 feet. Okay, question 15. All right, so as I'm looking at this, I see that these one angle, 2 angles, 3 angles, 4 angles make up 360, a full turn. So I also see this little square, so that means that it's 90 degrees. So we could make our equation 4x minus 5 plus 3x plus 35 plus 5x plus, don't forget the 90, equals a full turn, 360 degrees. So now combining the like terms, I've got 4x, 3x, and 5x. So that gives me 7, 12 x's, and just cancel them out after I've used them. Minus 5 plus 35, that minus 5 kills off this 5, and it becomes 0. So that's 30 plus 90 is 120, and that equals 360. So don't forget, we're trying to find x. So right now it's just a two-step equation. Get rid of the 120 from both sides. We end up with 12x equals 240. Divide both sides by that coefficient of x, and we end up with x equals 20. And so x would equal 20. Now arguably you could put degrees here. The reason why arguably is because really, take a look at its 5x. The 5x has the degree sign next to it, but x is technically just a number. So whereas this would be 5 times 20, giving you 100 degrees. So therefore, if you don't put the degree sign, it shouldn't be a problem. So that was question number 15. Okay, 16, again, we've got lines, and we're going to have to do equations here. So he wants us to find r, which is an angle. We will need degrees next to this one, and also find y. So whenever we have two straight lines or line segments that intersect, they create vertical angles that are opposite and equal. So we can start off by saying these two are equal. So 3y plus 10 equals 5y plus 2. So when we solve this, we look for the baby variable, which is over here, 3y. So we're going to subtract that. When we do that, we've got 10 equals 2y plus 2. Now it's a two-step equation. We just get rid of the 2. We've got 2y equals 8. Divide both sides by 2. We get y equals 4. So that's one of our answers. Y equals 4. Now to find out what r is, well, r is supplementary. It's a linear pair compared with any of these angles left and right. So if we take our 4 and plug it back in here, we're going to get 5 times 4 plus 2. So this is 22. So we just found out that this angle right here is 22 degrees. So r is the supplement to that 22 degrees. So this is 180 minus 22, and that gives us whatever r is. So the answer is going to be 158 degrees. So 158 degrees. And again, r should have degrees because it's the whole entire angle, whereas y technically doesn't need it because it's a component of this whole thing, or this whole thing, and those have degrees next to them. So that is question number 16. 17 again is transformations. We need to plot g, which is at 0, negative 5. So g is right here. And we have a number of degrees. We don't see a point, a center for the rotation, but we can assume that it's 0, 0. So we are rotating this 720 degrees. We also assume counterclockwise. 720 degrees counterclockwise. Well, all the way around is 360. So if we do the same again all the way around, that's a total of 720 degrees. And so basically G prime is going to stay in exactly the same spot. So we can get rid of this mess. G prime is exactly in the same place. So that was easy. That was number 17. Okay, number 18. So when we're talking about shadows, often this is dealing with right angles as well. So a 6-foot man has, so he's 6, has a 3.5 foot shadow. So his shadow is here. So shadow is always measured to the ground. It's not this piece, it's really what's on the ground. And we also know at the same time that a tree had a 10-foot shadow. Okay, so we got a tree, and this has a 10-foot shadow. And it says find the height of the tree to the nearest tenth. So let's call it h, height of the tree. And so hopefully we can see that both of these are right triangles. And also, because of how these shadow problems work, this other angle within the triangle, these two angles are congruent. And the reason why these two angles are the same is because the sun being so far away, as the rays hit the earth, we can assume that they are hitting the earth at the same angle. And so whether you're a person standing up or whether you're a tree, the shadows that are created on the floor all are similar triangles, because the 90 degrees are the same, and then also this sun's ray angle is also going to be congruent. And so this is our similarity postulate, a triangle similarity postulate. Angle, which proves that these two triangles are in fact similar. So that's going to help us solve this problem. We have two similar triangles, and so if we get rid of the tree, you could say this is 3.5 and 6, and this is 10, and h. So there's a couple of ways you could do this. You could set it up as h over 10, height over shadow, equals 6 over 3.5, height over shadow. Or you could say height to height. You could say h to 6 equals, so this is where we're matching up corresponding sides, equals 10 to 3.5. So at this point we could think about cross multiplying, but as soon as we times both sides by 6, we get h equals 60 over 3.5. And because the question says to the nearest tenth, question 18, nearest tenth, this is going to be 17.1. That's going to be our answer when you do it on a calculator. 17.1. And also units, feet. That was question number 18. Okay, 19. Again, another transformation question. Alright, so first thing to do is to plot t, which is at 2, negative 4. 2, negative 4. And that is t. And then it says, perform the following transformation, which is a negative 180 degrees. Well, first thing, we don't see a point or a center of the rotation, so we're going to assume it's the origin right here. Next thing, it says negative, so whereas we would usually go counterclockwise, we would now go clockwise. But another thing to note is that when it's 180 degrees, if you turn 180, it doesn't matter whether you go clockwise or counterclockwise, because you're still going to end up in the same place. So that's one thing to note. The other thing is that the two ways that I use to solve these is that at the moment this is 4 down and 2 across. So when we rotate first 90, we go 4 across, and 2 up. And then we got to do the same again, 4 across and 2 up. So now it's going to be 4 up and 2 across. So that gets us to this spot. That's one way that we could do it. The other way that we could do it is to remember the rule, which is when you rotate 180 degrees or negative, like I say, it doesn't really matter, it's the same thing. Our x comma y, the rule is that we negate both. It becomes negative x, negative y. So in our case, we had 2, negative 4. So when we negate both, our 2 becomes negative, and when we negate negative 4, it becomes positive 4. So this is going to be our t prime. Negative 2, positive 4, and label it t prime. And as you can see, that's where we got just by counting the squares as well. That was question number 19. Okay, 20, we're starting with negative 3, negative 5. So let's plot that point. Negative 3, negative 5, right here, L. Now, this time it's a compound transformation, and so the second thing that we see, we must do first. So in this case, we're going to reflect it over y equals negative 2. So y equals negative 2, we go to our y-axis where negative 2 is, right here, and we basically draw a line right across. And I'm going to put the arrows on because technically it's a line, right? And also I'm going to label it. This is y equals negative 2. And first thing is to do this reflection over this line. So at the moment, L is 3 jumps. 1, 2, 3 jumps to the line. So we're going to go another 3. 1, 2, 3. So this is where L would go. And next we've got to do this translation where we go 4, negative 5. So that's 4 in the x direction. 1, 2, 3, 4. And then negative 5. 1, 2, 3, 4, 5. So L prime is here. When it says negative 5, that means we're going to go down 5 because it's the second number that we see. So that's our y, up or down. That's our final answer for 20. Okay, question 21. So here we got a triangle and a triangle, and most of the time these are similar. So what I like to do in these cases is I like to separate the triangles. So I'm going to start to separate them here. A, B, E, and then we got the bigger triangle, which notice it shares angle A. Not B this time. A, C, D. So I'm going to label that because they do share this top angle. The other things that I'm going to label, well, we're told that BE is parallel to CD. So that tells us a whole bunch of things. It tells us, in fact, that this angle here is the same as this one, because this is almost like your transversal, and these are like your parallel lines. So these are corresponding, so we know that angle B is congruent to angle C. So straight away, we know two angles are the same, so we know these shapes are similar. We also know if these are parallel that E is the same as D. So we could label those two. E is the same as D. All right, what else are we told? Let's change the color, change it up to green. We're told AB is 3 and BC is 2. So if this is 3 and BC is 2, so that means the distance between A and C is the sum of those two, which is 5. So that's why I like to separate these triangles so I can see this more clearly. Next, we know that BE is 5, and we're trying to find CD. So BE is 5, and CD I'm just going to label as X. So now I can match up the corresponding sides. 3 compares with 5 as 5 compares with X. So I create my two ratios because these are proportional shapes, and I let these ratios equal each other to give me a proportion. So now by cross multiplying 5 times 5 and then X times 3, I get 25 equals 3X. Divide both sides by 3, and I end up with X equals, now 3 into 24 is 8, so it's 8 1/3. But because the question says round your answer to the tenths place, we should really write this as X equals 8.3, and that's 1 decimal place. Even though we would usually put 8.3 recurring, it does say 1 decimal place, so we can round it to this. And that's our answer for 21. Okay, question 22. What is the size of an exterior angle of a regular octagon? Well, in a regular octagon, there's 8 sides. Now, I don't need to draw it this time because for polygons, exterior angles, the sum is always 360 degrees. And when we're talking about exterior angles, let me just draw a few sides. We're talking about exterior angles, we're talking about these angles here when we stretch them out. These angles going all the way around, the sum of all of those, no matter whether it's a hexagon or a quadrilateral or a triangle, the sum is always 360. So if the sum's always 360 and we've got 8 sides, that also means 8 angles. We just divide it by 8. So 360 divided by 8 is going to give us our answer of 45 degrees. So 45 degrees is our answer for 22. 45 degrees. Okay, question 23, similar topic. What is the size of an interior angle of a regular nonagon? So as soon as we see nonagon, we know that the number of sides is 9. Whenever we see interior angles, we're thinking this equation, n minus 2 times 180. That gives us a total number of degrees on the inside. So it does say what is the measure of an interior, so it's one of these. So basically after we find our answer to this, we've got to divide by n, the number of sides or the number of angles, and that's going to give us the value of one angle. So when we plug all of this stuff in, we got 9 minus 2 times 180, all divided by 9. So this gives us a total final answer when you do everything on your calculator as 140 degrees. So that's our answer to 23. For 24, we got a polygon. In this case, it is a pentagon, 5 sides, 5 angles. However, not all the angles are the same, so it's definitely not regular. But we know that if this is a 5-sided shape, that our formula n minus 2 times 180 gives us 3 times 180, which gives us 540 degrees. So inside here, the sum of everything added up should be 540 degrees. Now another way to know that it's going to be 540 is that if you take your pentagon and you split it up, you know, I didn't draw it the best, but we're going to end up with 3 triangles. If I draw it a little clearer, when you split this shape up, you basically end up with 3 triangles, 1, 2, 3. And so this is also 180 degrees in each triangle times 3. And that gives us 540, just like we end up right here. Anyways, if everything's going to equal 540, we can just go around 2p plus p plus 30 plus p plus 35. We should remember that this is 90 right here. If you write it, you're probably going to save yourself from making a mistake. So the sum of everything is 540. Next, when we start to add all of these up, we basically end up, our equation simplifies to 4p, because you've got 2p, p and p, so that's 4p, plus 250 equals 540. So now it's a 2-step equation. Subtract the 250 and you end up with 4p equals 290. Divide by that coefficient 4 to get p on its own, and you end up with p equals 72.5 degrees. And again, it's arguable whether you need the degrees. P isn't an angle on its own, so you could just leave it as 72.5. That was our answer to question 24. Okay, 25 is interesting because you could do it the long way where you do 180 minus 3t and then you do the sum of these. But there's a rule that when you're dealing with a triangle, the exterior angle equals the sum of the 2 non-adjacent angles. So if one of these angles was here, you couldn't do this trick. But in this case, these 2 are non-adjacent, so we know that t plus 10 plus the other one, t plus 30, equals 3t. So combined terms, 2t plus 40 equals 3t. So now subtract the smallest coefficient of t, and you end up with 40 equals t. But now we've got to be careful because it says find the value of the exterior angle labeled 3t. It wants this value of the exterior. So we know that t is 40, so therefore 3t equals 3 times 40, so that gives us an angle of 120 degrees. That's our answer to 25. Okay, question 26. Alright, so here we're asked to find midpoint D. And D is the midpoint of CE. So you could plot this or sketch it out, or you could just remember the midpoint formula. So the midpoint formula is you sum your x values, x1 plus x2, and then divide by 2. So effectively you're averaging them. And then you sum your y values, divide by 2, so you're averaging those as well. So basically midpoint D equals the average of the x's, so negative 2 plus 4 all over 2, and then you're averaging your y's, 3 plus 9 all over 2. So midpoint D equals 2 over 2, which is 1, and really I shouldn't put my equals there, I should just put 1 comma 3 plus 9, 12, divided by 2, 6. This is the midpoint, 1 comma 6, and that's our answer for 26. Okay, 27 is related to 26. It wants to know the distance. So I'm going to write down what we had in 26, which was point C is at -2, 3, and point E is at 4, 9. So when we're looking for the distance between these points, we've got to use the distance formula. So D equals square root of x2 minus x1 squared plus y2 minus y1 squared. If you plot this or sketch this, you might be able to do it a little quicker looking at a right triangle and the Pythagorean theorem, but this is effectively the same thing. So the distance, which is CE, equals the square root of our second x, which is 4, minus our first x, which is -2, plus the difference in the y's, that's 9 minus 3 squared. So this equals the square root of 4 minus -2 is 6. So that's 6 squared plus another 6 squared. So this is 6 squared is 36. So 36 plus 36 is radical 72. So basically the distance D, which is really CE, or we were talking about CE, and so this distance is square root of 72. If we stick to the tenths place, 1 decimal place, then on a calculator this would give us an answer of 8.5 to the tenths. This would be our answer. So that's question 27. Okay, question 28 is looking at the ratio of the distance CD to DE. So sometimes there's more math involved in this, but let's just look at what we're trying to do. We have 3 points on a line, C, D, and E. We were told that D is the midpoint. So that means that CD and DE are exactly the same length. We also just calculated that C to E is approximately 8.5. Not that we needed it. And the very fact that D is in the middle means that this piece of the segment and this piece of the segment being equal means that they have a 1-to-1 ratio. So CD to DE, the ratio of those segments are 1-to-1. No other work is needed. Just 1-to-1 is the answer. Okay, question 29 has a few parts. We're going to look at the diagram below, create sentences using geometric notation to describe midpoints, perpendicular parallel segments or lines, angle bisectors, etc. So A is asking us for congruent segments. Well, I see this and I see this. So therefore segment BC, must put the line on top, is congruent to segment AB. So that could be our first statement. Next it wants another congruent segment. So I see these two. I see that CD is congruent to DE. And again, you could switch these letters around. That's not a big deal. Next, parallel lines. Well, these are the names of our lines, L and K, and we see that they've got these feathers, these little markings. So we can say that line K, lowercase script, is parallel to line L. Now there's another way you could write this. You could write line and then use 2 points like B and C that are on line K. So you could say line BC is parallel to line AE or AF or even EF. That would also work. So either one of those is correct. Next, D, perpendicular segments. So I see this is 90 degrees here. So let's go with that. We would say that CE, segment CE, is perpendicular to segment AF. And again, you could say EF, or you could even say line L. But key thing, perpendicular sign, just like parallel is important in part C. Midpoint. Well, the only thing that I can see as a midpoint is D, because it's halfway between C and E. It separates it into two congruent segments. So therefore I would say that point D is the midpoint, no short way to say this, of CE. So that's question 29. All right, number 30. So it says use a compass and straight edge to construct an inscribed equilateral triangle. So I'm going to try and show this without the live view of me using a compass. For extra help, look at the constructions videos I've made for inscribed shapes and for bisections or copying angles, all of that other stuff. But I'm going to try and demonstrate it, hopefully not too badly, right here. So basically using a compass, so we use a compass to make circles. That's one thing that we do with them. So I'm going to make a circle. That's not a circle. I'm going to make a circle here. Right, here goes. Alright, really I wanted the stroke. So you know what? I'm not doing too good with this tool, so I'm going to try and sketch this. It's going to be a little messy. So if here is my center, I'm trying to do a circle, I would use my compass to kind of make this. Next, I would keep my compass. So your compass has a pencil in there, and it has a point, and then usually you twist it here. I do not want to close this distance that this compass is open. I want to keep the compass the same distance from here to here. The radius, I want to keep it open the same. So I'm going to put my compass point on the circumference of the circle and go around the circle making little arcs. The compass point goes on the arc that I've just made, and then I make another arc, then put the compass point on the arc, then make another arc. Compass point, other arc, compass point, other arc. And before you know it, you've joined up the entire circle with 6 arcs, and then you've arrived back at your initial starting place. And then if we join up each of these arcs, we would in fact have an inscribed hexagon. But what we're looking for is an inscribed equilateral triangle. So what we would do in this case is we would join up every second one. We would skip an arc, and then this would give us a perfectly equilateral triangle that's inscribed, meaning it's just each vertex of the triangle is touching the circumference of the circle. And every angle, because this is an equilateral triangle, every angle would be 60 degrees. So do watch the live video of me holding the compass and making the marks. It might explain this a little clearer than just me using the sketch pad here. Okay, same deal with 31. The videos of me doing the construction are probably a little clearer, but let's try. So to bisect this angle, we would put the point at the vertex, and we would just make an arc with our compass. So it doesn't have to be too big or too small, it just has to be something reasonable on the page. The next step would be to put our compass at the intersection of the arc and one of the rays, and to make another arc here. Now we do not want to close our compass, we want to keep it open the same distance for the next step, where we now put our point of the compass here and then make an arc here. So we just want these two arcs to intersect, and the final step would be to join up the intersection of these arcs and also the vertex of the angle. And so what this does is it splits the angle into 2 completely equal pieces. So it bisects it. So now this part here would equal this part here. Those 2 last marks we don't need. What we see is our answer to number 31, bisecting an angle. Okay, Okay, question 32. Okay, so this is one of the toughest constructions. Again, the live video of me holding the compass is gonna be more useful, I think. But anyway, I can show you the steps here. We're constructing a parallel line to the given line that intersects the given point. So effectively, we want to end up with something like this. We want to end up with this. Now that looks pretty good, but when we're doing constructions, it needs to be perfect. And so we can't just eyeball it and guess. So here are the steps. The first step is to draw a transversal, which is a line that goes through one of the parallel lines. Later on, it's going to go through the other one. And it must also go through the point. The next step is to draw an arc with, let's choose the right tool. I'm going to draw an arc with our compass at this point, and the arc is going to pass through both lines. Now we don't want to close the compass, we want to come back up to this point and do exactly the same arc. Okay, so both of those orange arcs and points represent a compass not being closed. It was the same distance for both. The next step we want to do is we want to copy this angle. So in pink, I'm showing where we need to put the compass point, and we need to open the compass so that it can just make this arc right here. So I'm putting a little arrow. We need to just open it up so it's this distance. We then move it up to the other intersection of the arc and the transversal and do exactly the same marking. We don't want to open or close the compass. We want to keep it exactly the same. And the final step, which I'm going to show in green, is now we have these two reference points. We have here and we have here, and we need to join them both up. So that's exactly what we're going to do here. We're going to join them both up, and this gives us our parallel line through the point that we were originally given. So to recap, the red line was first, the transversal through the point. The orange was next to do these two arcs with the point of intersection of the transversal and the original line, and also the point that we were given. Then we did the pink where we opened the compass up to measure this angle. And then finally, the green line goes through the intersection of the mini arc and the point. And we just constructed a parallel line to the first line that intersects the given point, which is underneath there. Okay, number 33 and number 34, I put them both together. These are just asking us for the postulates that we need to remember. So when we're dealing with congruency postulates, they are different to the similarity postulates. The congruency postulates are side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse leg. We do not want to remember the donkey rule, which is angle, side, side, which does not prove congruency. So if you're confused with what these mean while you're watching the review, then maybe go back to watch the individual video on congruency postulates or similarity postulates, and they'll explain exactly what we use these for and exactly how we identify them. Okay, 34, the three similarity postulates. Well, if we know two angles are the same in two triangles, then we know that the third angle is the same. And if we know all three angles are the same, then we know that the shapes are similar. So two angles, we know two triangles are similar, which means all the sides are in proportion and all of that other stuff. The second one is side, side, side for similarity, meaning that if we've got two triangles, but the sides are in the same proportion, like 2 to 4 matches 3 to 6, matches 4 to 8, we can see that these sides are in proportion. 2 to 4 does equal 3 to 6, does equal 4 to 8, because they all simplify to become 1/2. So side, side, side for similarity isn't the same as side, side, side for congruency. Here, all sides must be congruent. Here, underneath, all sides must just be similar, meaning in the same ratio. And finally, side angle side for similarity, meaning two sides must be in the same ratio and the angle must be congruent. So angle congruent, sides similar. That was 34. Question 35 is the last question. Here we're asked to state if these triangles in A, there's two triangles, to state if they are congruent or if they are similar or neither. So let's take a look. One of the first triangles we see is ABC. The other triangle that we see, well, let me write it in order because here we got one mark, and then after we go A to B to C, we go past the 1 and then past the 2. So this other one is E to B to D, just keeping the same order, past the 1, past the 2. So at the moment we see two matching sides. That side matches this one. We see this side matches this. And then the key to this question is knowing that we have these two angles which are in fact congruent because they are vertical angles. They're created by two intersecting line segments. So therefore we have side angle side, side angle side. Everything is congruent. So therefore we know triangle ABC is congruent to triangle EBC, and the reason is by side angle side. And that's 35A. 35B, well, I'm so used to separating these triangles when I see triangle and triangle. So I'm going to do the same. This is ACE, this is the bigger triangle. They both share this angle here. And then the smaller one is BCD. Again, it's a right angle. And then keep in mind these two angles are also the same. So we can see visually that AE is not the same size as BD. It's not to scale, but it's not the same size. And looking at our diagram above, we know we've got a right angle which matches this right angle, and we've got this other angle which matches this other angle. So therefore we know that these two triangles are similar, and they're similar because of the angle-angle postulate, but we just have to be careful how we write it. So triangle, let's do triangle AEC, so we go from here to here to here, is similar to triangle BDC, so we're following the same pattern, BDC, so we went from no named angle to 90 to two strokes, to two arcs. We did the same no name to 90 to two strokes, and the reason for this is by angle-angle. So that completes the midterm review. Hope it was useful. If you're still lost on anything, go back, take another shot, pause the video. Also leave comments below, and hopefully it's helped you with something. Subscribe and give it a thumbs up if it was useful. Many thanks.